So in general relativity, we do not have conservation laws of energy and momentum or angular momentum. And for good reason. The reason is that, according to Noether's theorem, any symmetry comes with a conservation law. Translation symmetry comes with momentum conservation. Translation in time symmetry comes with energy conservation. Isotropy, rotation symmetry, comes with angular momentum conservation. And when space-time is curved, generically curved in space and time, then there ought to be no translation, rotation, or other symmetry, generally no killing vector field, and so we don't expect a conservation law. But it would be so nice to have one anyway. For example, when we observe the collision of galaxies. Galaxies do this all the time. It's a quite frequent occurrence that galaxies would collide. And for example, when two spiral galaxies collide, then typically they will unite and end up as an elliptical galaxy. But the collision of two galaxies is hard to calculate, because if you can't rely even on the conservation of energy or momentum or angular momentum, how do you even make global statements about what might happen? By the way, did you know that our galaxy too is on a collision course with Andromeda? I think it's, what, 2 billion years or so that it'll take, and then Andromeda will be really big in the sky. But I think there's no risk really that stars would collide. That happens very rarely. I mean, the stars are typically on the order of light seconds across. That's the size of a star. But they tend to be on the order of light years apart, so they tend to miss each other. Anyway, so it would seem that it's very difficult to calculate, to use conservation laws, to try to use conservation laws to calculate astrophysical processes such as these. And of course, gravity is not negligible in those cases, so it would be a bad approximation to say gravity is weak. It's not. That's why they are colliding after all. However, there is still a way we can use conservation of angular momentum, and energy in a certain sense. The overall idea is this. Imagine that this is an isolated incident, and the universe, aside from that, is really flat and really empty. In this case, this is happening on the background, and I'm idealizing here, this is happening on a background which is translation invariant in both space and time, and rotationally invariant. So in the bigger scheme of things, globally speaking, not locally, but globally speaking, we ought to expect something like energy and momentum and angular momentum conservation. Even if it's not local, maybe we can calculate some global energy, some global momentum and so on that would be conserved just on the basis of the observation that globally everything is happening in a Minkowski space that has all the symmetries. So today we'll pursue that idea and see how we can do that. In the process, we will find out what happens to the Newtonian concept of gravitational energy. According to Newton, gravitational energy is just like Coulomb energy, 1 over r. In gravity doesn't have a potential. Gravity doesn't show up in the energy-momentum tensor. Gravity is the other side of the Einstein equation. It is not in the energy-momentum tensor. So when our aim is to develop balance equations for energy and momentum, conservation equations for energy and momentum, we will have to take into account the energy, so to speak, in quotation marks, the energy stored in the gravitational potential. And similarly, momentum that might be in gravity. This is alien to general relativity in principle, where gravity itself is curvature. And matter is a different story. Matter contributes to energy and momentum, but curvature is a separate thing. So what we are trying to do here is take something from the left-hand side of the Einstein equation, namely curvature, and reinterpret it on the right-hand side of the Einstein equation as gravitational energy momentum. And then see whether we get a conservation for that. And concretely, this is an important problem, for example, to calculate the dynamics of galaxies, because, not just because we're interested in collisions, but because this gives us insights into dark matter. Most of the mass in those pictures is not visible. From the dynamics of these galaxies, we know that there must be much more mass around than can be accounted for in the stars. And if we can understand better the dynamics of the masses, we can better trace where the dark matter sits and what kind of objects it is made of. Remember that here are the percentages. About 72% of all the energy in the universe, 72% of the average energy density is in dark energy. We are already dark energy dominated. The visible matter makes up only 5% of the energy that there is, and 23%, roughly 23% of all the energy density in the universe is due to dark matter. So it's a big chunk to study. And remember, dark matter has probably nothing to do with dark energy. Dark energy is what is proportional to eta mu nu. Dark energy is positive energy, negative pressure. Dark matter, on the other hand, is the missing matter to account for the weird dynamics of galaxies. And it is thought of as conventional matter, not with negative pressure. Positive energy density, positive pressure. We don't quite know what the equation of state parameter is for dark matter, but it's not inflationary. So in order to get to the bottom of what dark matter is, we need to understand the dynamics of big astrophysical objects such as colliding galaxies, and for that it's very useful to have conservation laws, or at least global conservation laws, even though we can't have them locally. Global in the sense that, there's only stuff going on inside a big Minkowski space, and that Minkowski space has symmetries. There is a caveat that I'd like to make you aware of right away before we dive into it, which is that it may often be a good approximation to say that the two galaxies that we are considering are embedded into an asymptotically flat universe, even though we know it's expanding. So that might be a good approximation to say that. But there's an extra issue that needs to be addressed in principle, which is that those galaxies might be radiating off something unusual that's very difficult to take account of, and that's gravitational waves. So we'll get back to that a little later, because the gravitational waves, they can screw up the idea that outside of where the two galaxies collide, it's just flat. It's just Minkowski space. It's not, because you have these ripples that might, in principle, carry away what we will now identify as gravitational energy. And of course, that a Nobel Prize was given for the discovery that binary systems really do radiate away gravitational waves, that they in spiral, because they radiate away gravitational waves, which radiates away energy, and therefore they get closer and closer to each other. That has been measured with enormous accuracy. I think it's at the moment the most accurate measurement ever of anything that's been predicted with that accuracy as well. It's more accurate than the G-2 in quantum electrodynamics. Okay, so now conservation laws, global conservation laws. We'll use the tetrad formalism. It allowed us to choose bases in the tangent spaces independently of the choice of coordinates. We can have that the metric has always this form, which was useful in particular to get the Dirac equation on curved space-time. And the tetrad formalism is useful to re-express gravity as a gauge theory, which is of interest for quantum gravity. The tetrad formalism is also useful because in the tetrad formalism we also allowed ourselves to express tensors in terms of differential forms. We identified differential form parts of these tensors, and so we had tensor-valued forms. And the point about identifying forms is more than just nomenclature. It's a deep thing. If you have a P form, you can integrate it over a P-dimensional manifold. And only P forms can be integrated over P-dimensional manifolds. And they could be tensor-valued forms too. So when we're interested in, for example, a energy momentum 4 vector, P mu, and we want to integrate that over a region, we need something that is integrable over that region. So we need a differential form that takes values in tensors or vectors. So we'll find it useful to use the tetrad formalism in order to tally up the gravitational energy in quotation marks over a region in which, let's say, two galaxies are colliding. Here, this is what I said earlier, that in special relativity, conservation laws arise from the translation and rotation symmetries of space-time. In general relativity, we have this equation here, which, however, does not express a conservation law. It is a Bianchi identity. It follows from the diffeomorphism invariance of the theory, and that is by construction always the case. It doesn't express any particular property of the space-time manifold. So it doesn't imply any conservation law. Of course, if we do have killing vector fields, then this can be turned into a conservation law, but on a generic curved space-time, we don't have that. Here is the idea then. In regions of significant gravitational effects, for example, where two galaxies interact with each other, there is no killing vector field. It's just too messy a situation to have any kind of translation or rotation or boost symmetry. But what if we consider that system to be inside a box, a really big box if necessary, and that big box is a three-dimensional chunk of space-time at a particular time. So we're taking a snapshot, and at this point in time, we're drawing a huge box within which are the two galaxies that we are considering. Within the space-time picture, within four-dimensional space-time, this is a three-dimensional hypersurface. Or, I mean, yeah, not infinite in extent, just a three-dimensional submanifold that's space-like. We choose the box large enough so that space-time is essentially flat at the boundaries of the box. So at those boundaries, we assume that space-time is, at those boundaries, we assume that space-time is flat. Basically Minkowski space asymptotically. Then we could expect that there is such a thing as the total box energy or the total box momentum or total box angular momentum, and hopefully we can show that these quantities that we can obtain by integrating over the entire box are constant in time. That would be really helpful. If we can define a total box energy and prove that later on it's still the same amount. It may be differently distributed in the box, but it's the same overall amount. A box energy, a box momentum. Now, from Newton we know, I mean in Newton's theory this would be true, but we know that from Newton's theory that what it takes to have a conserved total box energy in the case of galaxies is to tally up the kinetic energies, all kinds of energies that arise, including the gravitational energy. That's what we would do in Newton's theory. And clearly in general relativity, it cannot suffice to simply add up only the kinetic energies and then hope that that would be a constant in time. So we'll have to do a similar thing in general relativity. But what is gravitational potential energy? There surely is no scalar that would play the role of a gravitational potential. There is in some approximation for weak gravity, but in principle there cannot be any scalar potential. And in any case, there cannot be, even tensorially, there cannot be a gravitational potential. It's not just that it cannot be scalar, because gravity is tensorial. No, there cannot even be a local tensor that describes the local gravitational energy. And that's because locally, at any point, we can make the Christoffel symbols vanish. So if the gravitational potential was anything in terms of the gravitation of the Christoffel symbols, that couldn't be it either. So what we must expect is that in general relativity, if gravitational potential energy in some sense exists, then it has to be non-locally defined. You have to integrate over the box to get it. And secondly, we have to allow for the possibility that some of it might escape our attention, because some of it might be in the form of gravitational waves. In the case of Newton, there would be no problem. You just tally up the kinetic energies and the potential energies, and that's it. It will be conserved in time. But according to general relativity, if there is such a thing as gravitational energy, we should expect that it can leak out of the box. And if it leaks out of the box, we should expect that the conservation of it within the box is violated. We will, for the moment, neglect that possibility of leakage through gravitational waves, and we'll come back to it at the very end. Okay, so gravitational potential energy. There is no such thing locally as a tensor, because if it were a tensor, then if it's there, it would have to be there in any coordinate system. But we know that we can make gravity go away locally. Christoffel symbols vanish. So let's pursue this strategy. Let us reformulate the Einstein equation. Here's the Einstein equation again in the tetrad formalism. Remember, this is the energy momentum tensor, but one of its two indices is viewed as a differential 1 form. We apply the Hodge star to it, and then it becomes a differential 3 form, which is actually covariant vector valued. It's a covariant vector valued differential 3 form. Here we have the curvature 2 form. Remember, it's really just a curvature tensor with its 4 indices, but 2 of the lower indices were antisymmetric, and we interpreted them as a differential form. Again, why we do that is because it makes it integrable. Differential forms can be integrated. And here, this h, or actually it's the capital eta in the Greek alphabet, was defined as the Hodge star of the wedge product of 3 basis vectors of our frame. So these are basis vectors in the cotangent space. We take the wedge product of 3 of them, take the Hodge star of it, that's a 1 form. So overall, we have here a 1 form, differential 1 form, differential 2 form. The wedge product of the 2 is a differential 3 form, and that's what we have here too, differential 3 form. So this was the Einstein equation in the tetrad formulation. It's really just the usual curvature here, energy momentum over there. And we want to reformulate that, rewrite it, without any approximations, just rewrite it in such a way that we have on the left-hand side the d of something. Doesn't really matter what it is. We just need to know that it's the d of something. So we have an exact form on the left-hand side. And on the right-hand side, we have this, of course. But we also have some other things. So we rewrite the Einstein equation in such a way that we split the left-hand side, the curvature part, into something that is an exact form, and the rest we throw on the right-hand side and say it belongs to the energy momentum tensor. And that will then play the role of the energy momentum, the contribution to the energy momentum tensor from gravity. We'll just interpret it in this way. These contribution T alpha, these contributions will be called the Landau-Lifshitz differential three forms. So they will play the role of the energy momentum tensor of gravity. Einstein already was thinking in this direction, but there are some subtleties that Einstein hadn't seen yet. So for now, I will show you later how to do that split of the left-hand side into this. But what you may already appreciate is that there is some freedom in this. We take the left-hand side of the Einstein equation and we split it into the d of something, and the rest we put on the right-hand side. That's not unique. For example, you could put the d of 0 and then put it over here, and then we would not have done anything. So there is some ambiguity in how we do that split. And we'll have to fix that ambiguity. There will be a best choice for doing that. Which is the fact that we do have an ambiguity has to do with the fact that it's not unique what we write as the gravitational energy, the gravitational momentum. Well, technically, maybe I can give that away already, what it amounts to is this. Remember, the energy momentum tensor is symmetric. It has two indices. I mean, one of them is suppressed because we view it as a one form, but it really has two indices. And what we get over here is not necessarily symmetric. We will choose the split of the left-hand side into the d of something plus something else that we put on the right-hand side in such a way that the gravitational contribution to the energy momentum tensor is itself also symmetric, so that we keep the symmetry of the energy momentum tensor. I'll tell you in a moment why. Okay, so then we have the old-fashioned energy momentum tensor that comes from matter and radiation, and we have this new-fashioned Landau-Lifshitz energy momentum tensor that's gravitational in origin. We define the sum of the two as tau, and that's an energy momentum tensor one form, which obeys, it's the sum of matter and radiation energy momentum and the gravitational, and it obeys this nice equation here that d of something, the left-hand side, is equal to 8 pi g square root of g, and then that total energy momentum tensor. I'll show you in a moment what these T alpha are going to be, but let's for now just take it for granted that we can do this split. We will get some T alpha. What then? Well, then the sum of the two obeys that equation, and the d of something is always vanishing. D squared is equal to 0. So if we take the d of that entire equation, we obtain that the d of the right-hand side is vanishing. The exterior derivative of the right-hand side is vanishing. So we obtain that the d of square root of g star T alpha is equal to 0. By the way, we have not used that the frame is orthonormal at this point, which is why I'm keeping the square root of g. It may not be 1. Okay, so what we have obtained so far is that from the reformulation of the Einstein equation, we deduce that this total energy momentum tensor, that is the sum of the matter part and the gravitational part, obeys this equation. It's an exact form. But now we can use Stokes' theorem. Because we have the d of something is equal to 0, let us use Stokes' theorem. We integrate over some region d, and we integrate over the boundary of that region d in space-time. You see, this is a 3 form. I mean, the tau itself is a 1 form. With the star, it becomes a differential 3 form. The d of it is a differential 4 form. So we can take that thing and integrate it, because it's a 4 form, over a 4-dimensional space-time, a 4-dimensional region in space-time. That's what we will do here. We integrate over a 4-dimensional region in space-time, the d of nu, this being nu. And by Stokes' theorem, this is equal to the integral over the boundary of that 4-dimensional region in space-time of just nu. So integrating this whole thing over a 4-dimensional region in space-time is equal, by Stokes' theorem, to the integral over this part only over the boundary. And here it is spelled out. So we integrate over the entire 4-dimensional region, over an entire 4-dimensional region of space-time, this entire thing here, and then just that bracket appears here on the right-hand side. We integrate that over the boundary of that region. And again, let's check that the dimensions are right. Here we have a 1 form. The Hodge star turns it into a 4 minus 1 form, so a 3 form. And that's, of course, just a 0 form here. So overall, it's a 3 form, and we integrate it over the boundary of a 3-dimensional region D, which is 3-dimensional. So that's fine. Now let's choose a region on purpose. We choose the region D that we integrate over to be bounded by our box B. Remember, we had the 2 galaxies, and we considered them to be inside a huge spatial box. This huge spatial box is B. And we turn it into a space-time region, D, by just adding to the box an interval in the time dimension. So this is space, this is time in that picture, and our box is represented by just a line here. That's just the box. That's the box at an early time. That's the box at a late time, because this is the time direction. And so the spatial box times the, the temporal extent of it, that gives us a 4-dimensional space-time volume. That's our D. So this is time t1, this is time t2. That's the box, that's the box. We are assuming here that these events far out, see, this is the boundary of the box, and that's another boundary of the box. Those events are so far out, so far away from the galaxies in the middle of the box, we assume that these events are so far out that out there the curvature is already negligible, and space-time is basically Minkowski. So then we obtain that our equation cross, namely here this one, the application of Stokes' theorem, takes the following form. 0 equal to this integral over the boundary. Right? Never mind this piece that's vanishing anyway. So it's the integral over the boundary. We obtain that if we take this is equal to 0 for that particular geometric arrangement, it becomes the sum of 3 kinds of contribution. We have to integrate over, just a sec. Oh, much better. Okay. So the boundary of our 4-dimensional chunk of space-time consists of the box at the early time, the box at the late time, and this particular boundary out there, which is far away and along the time direction. So we can write the integral over the boundary as the integral over the box at the early time, that's this piece, plus the integral over the box at the late time, that's this piece of the boundary, plus the integral over this and that. We just combined it two into one symbol. And of course, it's all connected because it's really a three-dimensional thing, this box. I'm suppressing 2 dimensions here. So that set of events, capital T here, is far out, spatially far out, so far that the gravity no longer matters, and we are suppressing, we are just not considering gravitational waves at the moment. We are assuming that they are not generated in significant amounts. Okay, so our equation then is that 0 is equal to the sum of those 3 contributions. And the third one, we just argued away. This contribution doesn't matter. And why is that? I'm saying that the integral over this and that is 0. The reason is that it's an integral over square root of g times star of tau. Tau is the energy momentum tensor that contains both the old-fashioned energy momentum tensor of energy of matter and radiation, plus it contains that piece that came from the curvature. It contains that piece that came from the left-hand side of the Einstein equation. And both of those contributions vanish on T. The contribution to the energy momentum tensor out on T, so far away from the galaxies, the contribution that comes from the matter and radiation is vanishing because we are assuming that space is empty out there. And the gravitational contribution to the energy momentum tensor, gravitational potential and gravitational momentum, is also vanishing because we are assuming that space is flat out there. We're not allowing gravitational waves either. Okay, so what we have then is that Stokes' theorem has now given us that the sum of only those 2 terms is vanishing. It used to be 3. It used to be these 3 terms, the integral over the entire boundary. Now we just have to consider the integral over the box at an early time. So here we're integrating stuff over the box at the early time. Here we're integrating over the box everything that's inside there, gravity and matter, over, at a later time. Now you might think, that's almost a conservation law. It says that if we integrate matter and curvature contributions to the energy over the entire box at an early time, then this is the same as if we integrated it at a later time, except for a minus sign. So it looks weird, right? It looks like the energy flips sign as we go from an early time to a late time. Does anybody see how that's resolved? Well, it's because when you define the integration over a boundary, then it involves a direction vector for your boundary. And if you choose it inwards pointing, as is the convention, then its inwards pointing is future pointing for this surface, but inwards pointing for this surface is past pointing. Therefore, if we calculate everything future pointing, then we have a sign flip for the second contribution. And that just means that if we integrate this future pointing, then we get a minus sign here in front, which means we actually get, the F means future pointing, we get an actual conservation law. We integrate the matter and gravity contributions to the energy momentum tensor over the box at an early time, we get the same thing as if we integrated at a late time. And I shouldn't just say energy, it's energy and momentum, right? So now we can define the total ADM for momentum. ADM is the acronym for Arnold, Deezer, and Misner. So the total ADM for momentum is defined as the integral over the big box of this thing. This is the quantity that we just showed is conserved from early times to late times. And it carries only one index here, right? So we are integrating this. The 3-form part of it goes away because we are integrating over a three-dimensional manifold, a 3-form, and this mu index is an extra index, an extra covariant index that's left over, so we have a 4-vector here. And that 4-vector is conserved in time. The zero component would be interpreted as the combined energy and matter energy, radiation energy, and gravitational energy. And similarly, the I components are interpreted then as the momentum contributions from both matter, radiation, and from gravity. This p mu is, of course, not a vector that sits in the tangent space of any particular point of the manifold. However, it will transform like a Minkowski space 4 vector under gauge transformations, under Lorentz transformations, which asymptotically are global Lorentz transformations outside the box and in the region outside the box. That was the advantage of choosing to embed the collision of the two galaxies in a space-time that's asymptotically Minkowski space, where we have asymptotically Lorentz transformations. And that's one of those vectors there. I'm giving more details there in the small print. But then, this is all good and fine, but what is T alpha? All I've said so far is that if we can take the Einstein equation and rewrite it in such a way that on the left-hand side we have the d of something, and on the right-hand side we have the t star, we have the hot star of t plus something that we can write as the hot star of some other t, then this other t we will interpret as gravitational contributions to the energy momentum tensor. And then we showed that, yes, if we can do this, if we can just do this step, then we are in business. Then we will have a conservation law because the d squared is always vanishing. So if you apply d to the entire equation, you get the left-hand side is vanishing, the right-hand side is the d of something, and you can apply Stokes' theorem, and bang, you get the conservation law for the sum of these two things. But how do we get that? How do we go from this formulation of the Einstein equation to that reformulation? Something that Einstein already started. Okay. And also, it's not going to be unique. It's not going to be unique how we split what is in the left-hand side into the d of something and a rest which we put over there. How can we fix that choice? So the T alphas are not unique. The gravitational energy momentum tensor contribution is not unique. Now, there are various ways to argue. What I find quite convincing is that we want not only energy momentum conserved, but also angular momentum. And it turns out that for that purpose, the energy momentum tensor ought to be symmetric. By that, I mean the energy momentum tensor that contains both the traditional matter radiation contributions and the gravitational contributions. The split of the left-hand side of the Einstein equation into an exact differential form and the rest which goes into the energy momentum tensor is not unique. And depending on what we choose, we may or may not have a symmetry in the energy momentum tensor. So what we'll do is fix this choice such that, and it's actually unique, such that the new energy momentum tensor that contains both matter, radiation, and gravitational parts ends up being symmetric. So here's a proposition. There is a unique decomposition of the left-hand side of the Einstein equation such that the gravitational contribution to the energy momentum tensor, which for the purpose of the tetrad formalism we write as T index alpha, which is, however, a one form as well, so it has two indices. So if you spell it out, it's this, such that this T alpha beta is symmetric. And it turns out that for this decomposition, we have that the T alpha, the remainder that we have to take from the left-hand side of the Einstein equation to the right-hand side, that gravitational contribution to the energy momentum tensor, which is then called the Landau-Lifshitz 3 forms, is given by this lengthy expression here. It's an expression that involves this capital eta symbol, which is the hot star of the fourfold wedge product of the frame vectors. That's something innocent, obviously. It's very simple. It's just a notation that is a little shorter than that. And then it involves the connection 1 form. And what you can see from this is, I mean, ultimately we need to integrate this over in order to get the conserved quantities in the box. But let's look at it locally, because this is a local equation, right? This is a function of x and t. And all those guys are functions of x and t. And they involve the connection 1 form. And the connection 1 form is really, when you spell it out, the Christoffel symbol. And we can make the Christoffel symbol vanish at any point we want. And what this is saying is something that is consistent with intuition, namely that this is not really a potential. This can be made 0, right? We can, at any point, we can choose the Christoffel symbol actually to vanish. Gravity can always be gauged away locally. And this is just reinforcing that the conserved quantity is a global conserved quantity. It's not a local one. You have to integrate over the entire box to get this 4 vector, which then is conserved. But the individual contributions to this 4 vector, as you integrate over, they vary. They are gauge dependent. It's just the entire integral that is not. Okay, so this came out of the blue. I'll have to show you where this comes from. So we have to take the Einstein equation and split the left-hand side. Here again is the Einstein equation in the tetrad formulation. Energy 1 form, energy momentum tensor 1 form, and then this is the capital H, capital eta, is, if you remember, it's just, you take the wedge product of 3 frame vectors, theta beta, wedge theta gamma, wedge theta alpha, and then you put a star in front of it, the hot star in front of it, and you get a 1 form. So this whole thing is a 1 form. And here's the curvature 2 form. So you have a 3 form. Over here, this was the energy momentum tensor 1 form with hot star. It turns into a 3 form. Okay, so this is the Einstein equation. Next, we use the second structure equation. I hope you remember what the structure equations did. The first structure equation is the definition of the torsion. The second structure equation is the definition of the curvature. This is the curvature 2 form. And what the second structure equation is saying is that the curvature 2 form is obtained in this way. Maybe it's more familiar to you to think of the curvature tensor, the Riemann curvature tensor, which has 4 indices. And then it's expressed in terms of derivatives of the Christoffel symbols plus products of 2 Christoffel symbols. And that's what we have here too, if you spell it out. The connection 1 form can be expressed in terms of the Christoffel symbol. The D will differentiate it. And here we have Christoffel symbol, wedge Christoffel symbol, right? So it's the same thing, just in a more compact way in the tetrad formulation. So we're just expressing the curvature really in this way. Then let's plug that in here. Then we get 2 terms. We get that this term multiplies the capital eta, and that term multiplies the capital eta. Let us look at this term multiplying the capital eta. Okay, so here we have this term multiplying the capital eta. Let me see. Yes, right. So what we obtain is I made a mistake. I forgot the term here. Right. Okay. So if you plug this into here, then we get this term plus. This term is this times that, and then this term is supposed to be this term times that, and then equal to the right-hand side. So I need to put an h there. I'll fix that later. Okay, and then this term can be rewritten. In any case, I'm not giving you the full proof, which would be a few pages. I just give you the first step of two. This term now can be written as the d of the wedge product of both of them. So I'm re-bracketing. Instead of writing a d of the omega, wedge h, I'm writing the d of all of it. Okay, so it's the d of all of it. This will give us in particular, by the Leibniz rule, that term, but it will also give us a term where we have omega and then the d of h. So we'll have to subtract that term again. That's this one. But the Leibniz rule, because that's a one form, connection one form, we get a minus sign in the Leibniz rule. It's an anti-derivation. So actually, to subtract it is to add it in this case. So we have a minus sign here. Then, I don't know, this may not be very enlightening to go through all those details. So we have the dH occurring here from the D acting on the H here. That we can rewrite too, because if you remember, we showed in an earlier lecture that the absolute covariant derivative of D acting on that H gives us this, where the first term is the exterior derivative, and then the other terms are the covariant derivatives. Remember, the capital D, the absolute covariant derivative, is doing the action of an exterior derivative on the form part of a tensor-valued form, plus, that's this thing, plus it's doing the covariant derivatives on the tensorial parts of the differential form. That's what we get here. We plug that into our equation, and then the Einstein equation takes this form. And the message is, never mind the details, they're not so important. Message is that the Einstein equation is now the d of something, and then plus lots of stuff, which is not the d of something, equal to 8 pi g hot star of T alpha. So the left-hand side of the Einstein equation now takes the form of being the d of something plus some other junk equal to 8 pi g hot star of T alpha. All this other junk we now put on the right-hand side of the Einstein equation and declare it to be part of a larger energy momentum tensor. And on the left-hand side we have this thing, and we are in business because we now can take the d of the entire equation, the left-hand side goes away, and we get the d of the right-hand side is vanishing, apply Stokes' theorem, get the conservation law. This was the first step. The second step is to redo it, redo it again, this time to make sure that the T that we get, the extra T, the gravitational T, is symmetric. Because this is quick and dirty, but doesn't give us the symmetric T, so it needs a little bit of a fix, but the fix takes 2 pages and it's T just like this. So it doesn't really give big insights. But overall, the conclusion is that this is how we split the Einstein action into an exact form, not the Einstein action, the Einstein equation on the left-hand side into an exact form plus the rest. And we arrange it in such a way that that rest is symmetric. And then that's on page 112 in Straumann's book. I give you the page number on another page here of this lecture. And so we then have all the ingredients to calculate the ADM energy momentum vector for a big box. Namely, we integrate this thing where the T mu is the energy momentum, is the sum of the usual energy momentum tensor plus the T alpha that we just calculated, namely this thing. So you have to integrate over the box in which the 2 galaxies are, both the regular energy momentum tensor coming from matter and radiation, plus take the Christoffel symbols and work out that complicated thing and integrate that too. Add that to the total calculation, and that gives you the gravitational contribution to the effective energy momentum. Yeah, so both of those contribute here, and you get the P mu. Now, yeah, well, this is from gravity, and that is from matter and radiation. Remember that we had energy conditions, and for example, the weak energy condition was to ensure that the T naught naught of the energy momentum tensor, which is the energy density, is always positive. Even though the energy might not be conserved, the weak energy condition is saying we'd like this to be positive. And then we had the strong energy condition, which we needed for the Ray-Choudhury equation to show that singularities must form under certain conditions for singularity theorems. But we also had the dominant energy condition, if you remember, and we haven't used it yet. The dominant energy condition is the weak energy condition plus the requirement that energy flows only inside or on the light cone. It turns out that you can prove the following theorem. I mean, if the dominant energy condition holds, then the P naught, the energy in a box, the ADM energy in a box, is always positive. So the gravitational contribution might be negative. Remember, it's an attractive force, gravity, that would give us a negative contribution to the energy. But overall, in total, it comes out positive. That's actually very complicated. It's rather tedious to prove that. And Witten came up with a simpler proof, which is, however, still rather tedious. So let's not go through the details of that. So that theorem is called the positive energy theorem. It says that if the dominant energy condition holds, then a P naught is always positive. This is of significance not only for the study of galaxy collisions, but also for the purpose of studying the quantum theory of gravity. Now, you see, if for example the energy was not bounded from below, then the universe would be unstable, and you could have that matter just keeps collapsing while radiating off energy, and that would be not a stable situation. So how about angular momentum then? So we choose coordinates for that purpose, which become Cartesian Minkowski coordinates far out. In any case, we are assuming that we are having a flat space-time sufficiently far away, where the box ends. Minkowski space should basically begin. And then we can define a generalized angular momentum matrix, generalized not in the sense of something entirely new. It's just that it's both space-time. Remember that angular momentum traditionally just rotates in space. If you also want to include rotations in space and time, which is to say boosts, then you're not dealing any longer with the three-dimensional rotations. You're dealing with a four-dimensional object. And that these rotations and boosts are naturally in a four-dimensional matrix, where, I mean, it's a matrix, it's a square matrix where the two indices both run from 0 to 3. And as far as the asymptotic Minkowski space is concerned of outside the box, we can define an angular momentum matrix which transforms according to the Minkowski space Lorentz transformations for far outside the box in the following way. We take the x and the tau variables. So this is like the distance, and these are the like the momentum 4 vector. And this is a combination similar to that you would have for an angular momentum operator, xi pj minus xj pi. And this angular momentum, generator of Lorentz transformations, so that's what the angular momentum does, the generalized angular momentum of rotations plus boosts is generating Lorentz transformations. This object then obeys that condition, which is, we now know, the hallmark of a conservation law, because the d of something is vanishing, which means that we can go into the Stokes theorem. integrate this over a four-dimensional space-time chunk, and we obtain that this is equal to 0. And by Stokes' theorem, this is the integral over the three-dimensional boundary of just what is in the bracket. And so this calculation of the total angular momentum gives us a number, or gives us numbers which are conserved in the evolution of that box. And for this to work out, to go from this definition to that conclusion, we needed this T to be symmetric. Once we write out the two indices that it really has, then it has to be a symmetric energy momentum tensor. Then this becomes true. So that's how we fixed what has to be taken to the right-hand side. So the conserved angular momentum, ADM4 angular momentum, is what you get when you integrate this over the spatial boundary of our space-time region. So the box again, that is conserved then. All this was good and fine, but remember that we made the assumption here that at the boundary of the box and further out, we basically have Minkowski space. No matter, no curvature. We can't really maintain that strictly, because when two galaxies are rotating about each other, they are like two ducks in a pond, and they will create waves. And those waves cannot be stopped. They will just travel out and will cross the box. And in principle, they might carry gravitational energy with them. So how can we take that into account? There is no complete theory about this just yet. Also because we're really doing damage here to general relativity. We're making approximations. Nothing of this is exact. But for practical purposes, this is how this is being tackled nowadays. The idea is to reconsider what we mean by the box. See, when we defined the box, what we did is we, how far up is that? Okay, here's the box. What we did is we said, here is a space-like hypersurface. This is a three-dimensional volume in space. And we just look at its timeline, its evolution, and then we have the box here again. And that's just some space-like hypersurface. But there are many different kinds of space-like hypersurface. What we can do in order to prevent gravity waves to escape, or, I mean, they want to escape anyway, but what we can do to make sure the box contains as much as possible of them is to employ a trick. You see, in order to define a space-like hypersurface, we could have an army of astronauts, and they all have synchronized clocks. And when that clock strikes 12, then that defines a space-like hypersurface. These events, this astronaut here with that wristwatch there, and then his wristwatch, her wristwatch, and so on. And when it strikes 12, that's when we have, these are the sets of these events. And we are thinking intuitively of all those astronauts floating there peacefully. But what if these astronauts are actually on accelerated trajectories? What you can achieve by that is that you still have a space-like hypersurface, but it sort of bends upwards. A light ray that is emanating from the center of our box has a hard time catching up with one of the faraway astronauts, because this fellow is accelerating. It's actually very fast, right? So it's difficult for him to catch up. What you can do is you can choose your definition of space-like hypersurface in such a way that it bends upwards, which means that, and approaches the speed of light. Basically, the faraway astronauts are very, very fast. And in this way, only gravitational waves that are emitted right away could escape out of the box. All the others, have a hard time. By the time they would catch up with an astronaut, you might already be at a later time where you are already reading off the next time. So there is a way to choose the space-like hypersurfaces in such a way that they bend upwards, that gravitational waves find it hard to escape in time. So you just keep them in the box because you chose your box cleverly. When you do that, and I'm not going into all the details because it's a messy business, then you're basically capturing the contributions of the gravitational waves, but you are really changing the framework a little bit while you do that. It's not just what I said that you bend this upwards, and the form momentum that you then get is called the Sachs-Bondy form momentum. I'm giving it a superscript SB to indicate that it's not quite the same as before. So the message of this is that if you need to worry about gravitational waves, then it becomes more complicated. You have to be more careful. And if you know that the gravitational wave radiation is not going to be dominant, then go by the thing that we derived, and it's going to be more straightforward. Mm-hmm.
So is there a reason we can't say, start our initial space-like hypersurface to be where we have matter and gravitational waves and everything, our initial conditions, and then just have our surface expand, like have everything outside of that being vacuum, and then have it just...
Yeah, in essence, yeah, you could do that. Yes, that's right. And also, you might ask, don't we have the same problem with just ordinary radiation as well? It can escape too. Why is that not a problem? Well, that's not a problem because if, let's say, light energy is traveling outwards and crosses our boundary of our four-dimensional region and escapes therefore our attention, then we can account for that because we can locally measure how much energy is escaping through the boundary, right? Because it's well defined what the energy is at a point in time and space for matter and radiation. We can calculate it and subtract it. But for gravitational energy, you just can't localize it. You see, this is what makes it so difficult. We can't say at this point now this much gravitational energy goes through. We can only do it asymptotically from the perspective of somebody who is out there in the flat space. That's what makes it more complicated. All right, so this is as far as we got. I thank you for putting up with all the scheduling issues there. I think we still have a bit of time, and if you have questions, I'm happy to discuss. Also, if you could give me some feedback.
So for the D of the box you choose, can I just choose an arbitrary box without worrying about having a space-like hypersurface of B at the bottom, and then space-like hypersurface B at the top? As long as I can guarantee that the time-like parts of it has flat metric there, what's the problem of having an arbitrary shaped box?
Yes, you can. Stokes' theorem doesn't mind what you choose there. And in fact, that's what we did. You see, I drew the box at the top as a straight line, and the box at the bottom as a straight line, but with respect to what? Right? So it's not unique. You could choose any space-like hypersurface at the top and at the bottom. Now, what you could do is, of course, you could, as we saw with the Sachs-Bondy, right? You can bend these things up so that it's not just going space-like and then light-like, right? It could be in a more smooth way. But in principle, yeah, you could just draw a sphere. The Stokes theorem would still work. You're so quiet, as if we had just had terrible news or something.
Yes. I think I actually have an intuition for my question, but I still want to ask anyway. So do you have to account for sort of the Gibbons-Hawkins term that you have for like extrinsic curvature and all the sort of embedding if you're doing this sort of problems? Because you're taking like a box, right? So I assume that even for a lot of things you should have your embedding to integrate everything. And this
Okay, okay, so there are two things. One is, well, it's of course something that comes up in quantum field theory, and if you just do it classically, it wouldn't come up. But in quantum field theory, it's true that if you consider just a box, and that box might be human-made, so it's just mentally we put it in a box, or it could be something out there in nature, such as a horizon that limits a region. Then whenever you do this, and you confine your quantum field theory to just inside of that, then you have an excited state in there. And the reason is that in quantum field theory, as we will see in a lot of detail next term, in quantum field theory, the vacuum state is an entangled state. If you consider just a chunk of the vacuum, just a region in space, then it is entangled with the outside of that region. Which means that if you disregard the outside, if you trace over the outside, then the inside will no longer be in the vacuum state, it will be in a mixed state, because you've had entanglement, and if you trace over part of it, then you have in a mixed state for the inside. But the mixed state cannot be the ground state. Ground state is a pure state. So you have a state that's energetically elevated. It's a weird thing in quantum mechanics, but this is how it works. And this leads to Hawking radiation, it leads to Hawking-Gibbons radiation in the case of black holes, black hole horizons, or cosmological horizons. And in principle, even if you physically just put a box there, you have to elevate the energy in the box just by creating the box. So, and in principle, yes, that should contribute there. Absolutely sure, to the energy motion.
This globally defined energy and momentum conservation laws, they don't seem quite to have the full use I was hoping to, because what I'd like to talk about is we have two galaxies coming towards each other. They have some momentum each initially, separately, and then there's some sort of, after the interaction, one of them has more momentum than it did before. And so how do we talk about two different subsystems, both having momentum, and then afterwards having different momentum?
I suppose, well, see, I studied these things, but I've never applied them, so I am not sure. But I suppose you could, if the two galaxies start out far enough apart, so that you can assume in between them to have Minkowski space again, then that should work. But if you start out with them already so close that you can't have an asymptotic region in between, then I don't think you can do it. There's only the total that's conserved.
Okay, and I think that just corresponds to picking a surface that's like a pair of pants or something. But yeah, I think I see that.
Yeah, or preferably two pairs of pants, right? So, yeah, so that it's a scattering kind of thing.
Yeah. Okay.
Yes, yes. So by the way, maybe I should say something about the course that I will teach next term. It will not build on this term, on this course, because, well, the purpose of the course next term is to study quantum field theory on curved spacetime, but the amount of GR that's needed for that is really minimal. We need to know the Schwarzschild solution, we need to know Friedmann-Robertson-Walker solutions, and that's pretty much it already. You just need to know those solutions, those metrics, and then we will study quantum field theory in that background. So the focus next term will be entirely on the quantum field theory, and the GR will be trivial for you. And so we will study then the Andrew effect, namely how acceleration leads to the excitation of quanta, and the Hawking effect. And then eventually, and that will be, I think, the most exciting part of it, at least for me, is how structure in the universe came about. Namely, the idea of the current standard model of cosmology is that when inflation happened, it was, you had our universe spawned from another universe through a quantum fluctuation in the original universe. And this led to a flattening of space-time, driving it towards flatness. Remember that if the universe is inflationary, when it has an acceleration, then it's driven towards flatness. The energy density is driven towards a critical value. Only when it's not accelerating, then its dynamics is away from flatness. During inflation, it's towards flatness, and the assumption is that there was a dramatic, brief but dramatic period of inflation at the beginning of our universe, which flattened it completely, but, I mean, almost completely. But now we see, of course, a lot of structure in the universe. Galaxies here, galaxies there, and the statistics of the distribution of galaxies can now be measured with great accuracy. There are huge surveys, like the Sloan Digital Sky Survey, that measure the distribution of galaxies, and you get probability distribution for the distances and so on, two-point functions, 2-point correlate, 4-point correlate, and so on. And you find particular patterns in there. The statistics is highly non-trivial of the distribution of galaxies in the universe. It's homogeneous and isotropic, but non-trivial over the length scales. And it's consistent with the idea that the inhomogeneities in the distribution of matter that we see now in the universe arose from the inhomogeneities in the cosmic microwave background, which is the same universe but very much earlier. There were some inhomogeneities, and these inhomogeneities have the appropriate statistics to account for what we now see in the distribution of galaxies. But that leads to the question, where did the inhomogeneities in the cosmic microwave background come from? Given that the universe was supposed to be completely flat with extreme accuracy, like 1 part in 10 to the 40, some theories of inflation have it like 1 part in 10 to the 100 to the 100 or so. I mean, it's just, it's very, very flat. So how come that the cosmic microwave background has some significant inhomogeneities? It's about 1 part in a million. The temperature fluctuates by about 1 part in a million. It doesn't sound like much, but considering a period of earlier inflation, it's not clear where that comes from. And the theory that was proposed in the late 70s and early 80s by some people in Belgium and some Russians is that as inflation happened, not only was space flattened by the expansion, but also quantum fluctuations were ripped apart and made very, very large. It's an outrageous idea if you think about it, right? And what they say is that quantum fluctuations happen always everywhere. But they tend to be small. As we will study in the next term, quantum fluctuations happen with electromagnetic fields, with all kinds of fields. With electromagnetic fields, you can now measure them directly in the lab. It's not even expensive equipment. You can measure the vacuum fluctuations of the electromagnetic field. But they tend to happen only at small wavelengths. The smaller the wavelength, the larger the fluctuations. Now, when have you last seen a big fluctuation of the electromagnetic field of a wavelength of 1 meter? It doesn't happen, very, very rare. But for very small wavelengths, it's important. It accounts, for example, for the Casimir effect and so on. Right, so how could these people come up with the idea that those tiny quantum fluctuations are ultimately responsible for the distribution of galaxies in the universe? Right? And so the idea is that if you look at sufficiently small wavelengths, the amplitude of the quantum fluctuations is really large, quite significant. And during inflation, during that enormous expansion at the very beginning, those short wavelength fluctuations were simply pulled apart. Their amplitude was staying the same, but their wavelengths were stretched apart from almost to Planck length to galactic scales, even extragalactic, I mean, millions of light years across, even billions of light years. So the tiny quantum fluctuations were happening with reasonable amplitude, with very large amplitude even. Normally they would just snap back and we never learn about them. But during inflation, we stretch apart. In fact, it's a pretty solid prediction because even classically something like that happens. If you take an ordinary wave equation, be it the Maxwell equation or the Planck equation, but just classical, and you consider that equation on an expanding space, even on a balloon, if you like. So you consider the vibrations on a balloon and you blow up the balloon very, very fast. What you find is that the equation of motion, the Planck equation, will have it that if the wavelength that you consider is larger than the size of the horizon, then the wave stops oscillating. it freezes its amplitude. It's a classical phenomenon. It freezes its amplitude. And the quantum theory of that is the same. It just applies to quantum fluctuations. You have tiny quantum, you have small wavelengths, large amplitude quantum fluctuation, and during the period of inflation, it basically froze. In the Hilbert space, the dynamics froze. You had a large expectation value of the amplitude of those fluctuations, small wavelength, but the wavelength slots stretch. And then you end up with a situation at the end of inflation where you have these relatively large quantum fluctuations, 1 part in a million, imprinted on the early hot universe. And then where there are overdensities imprinted, matter will fall in and eventually form galaxies. And where there are underdensities, you end up with voids. Matter flows away to galaxies. So ultimately, the idea is that all structure, including us, go back to quantum fluctuations very early on. One of the most outrageous but fantastic ideas that has come up, I think, in the past decade. And remember too that one moment that in the 80s, this was just one theory out of many. And a major competing theory, which was, for example, advocated and developed by Neil Tork, the director of Perimeter, was that maybe the structure of the universe has a completely different origin. We know that the universe started out very hot. As it cooled down, it went through several phase transitions. And when phase transitions happen, then faults can develop. For example, if you take water, and you freeze it very slowly, then you get ice that is transparent, because it's a very, almost perfect crystal. If, however, you take water and freeze it quickly, then the orientations of the ice crystals don't have time to align themselves, and so you end up with lots of microcrystals with boundaries in between them where the crystal planes don't match. This is where light can scatter, and you get milky ice. So similarly, in the universe, all these phase transitions happened in a rush. It was cooling down pretty quickly. And so the idea was there could have been faults in the transitioning from one vacuum to the next vacuum. And so you have then one vacuum here, and then there's a boundary and another vacuum over there. And there could be interfaces of various dimensions. It depends on the gauge group of the interaction that is being undergoing the phase transition. So you could have cosmic strings or cosmic textures, for example, depending on the gauge group is. And those would be places, those interfaces between two different vacua would be places of elevated energy, just like in an ice crystal. The water goes into the ice form because it's energetically lower. But if the crystal is disturbed, then it's no longer the lowest energy state. If you have two crystal planes that are not quite aligned at the interface, the energy is elevated. So similarly, as the universe cools down and it goes through phase transitions, and they're not perfect, they're not slow enough to have the same ground state after they cool down everywhere, then at the interfaces of those different vacua, you get those cosmic strings or cosmic structures which are elevated in energy, and that means attractive. Matter would congregate about them, and you have inhomogeneities, and they could be causing the structure in the universe. That led to a fully developed theory that made predictions for what the statistics of the galaxies should be, what the statistics of the temperature fluctuations in the cosmic background should be, and it's not that. it's inflation was spot on, and that theory was not. Which isn't to say that it didn't happen, it just was the dominant. So it's still the phase transitions probably created some defects, but they are not dominating the inhomogeneities in the universe. And one advantage of this application of quantum field theory to curve space-time over Hawking radiation, which we'll also do, is that with Hawking radiation, nobody's so sure. It's just a messy business. But the cosmic inflation is not controversial. I mean, maybe that there's a more fundamental theory, but it will have to reduce the cosmic inflation eventually because it's just so successful in predicting things. So cosmic inflation is just how it is. It's a standard model. Whereas with Hawking radiation, even though it seems perhaps simpler because it's just about one little object, a black hole, as opposed to the entire universe, it's actually harder for a black hole.
The global energy momentum tensor that we get, what space is that living in?
But space?
Yeah, because it's not in the tangent bundle.
No, it's not a tangent bundle. Yeah, remember that we have asymptotically Minkowski space, and the 4 vector that we get is a 4 vector in that Minkowski space. That's what it is. You can actually allow yourself, in the calculation of these quantities, to do local Lorentz transformations inside the box. You can gauge that, it doesn't matter. But outside, that's where, with regard to the outside Minkowski space, is what it is. It's a 4 vector.
So gravitational waves can also blow up and freeze in.
Yes, yes, that's right. Oh
Oh,
yeah, sorry, you were next, right? But let me just reply that. Yes, the same is expected to have happened for gravitational waves. The impact of gravitational waves on the cosmic microwave background is, according to the standard model, an imprint on the polarization in the cosmic microwave background. Now, the polarization of the cosmic microwave background you can think of as a vector field. At every point in space, you measure in which direction is it polarized. And that vector field in the sky can be decomposed into a gradient and into a curve. The gradient has many astrophysical origins. It's quite contaminated to get relatively little information about the early universe from that. But the curl part of the polarization field in the sky is almost exclusively sourced by the gravitational waves, by quantum fluctuations in gravitational waves, very early on during inflation. That's why 2 years ago, when BICEP2 announced that they'd seen it, it was a big deal, because this would have been the first pretty much direct evidence for gravitational waves, and quantized gravitational waves at that. It turned out, though, that it's not such a clean signal, and there is foreground from our own galaxy. And where they looked through our galaxy, it was actually quite contaminated. So they cannot be sure that what they saw is really tracing back to the cosmic microwave background. It may be just some local galactic foreground. So they didn't prove either way. They didn't show it's big, they didn't show it's small, it's just inconclusive. But more results are expected. Now everybody's trying to study this, and we will find out how big this is. Actually, the situation is it's actually a little more complicated, and we'll, I cover that in some detail next term. In principle, we expect to have seen gravitational quantum gravity effects in inflation. And the reason is that when I said that the inflation field is quantum fluctuating, and its waves, its small wavelength quantum fluctuations of large amplitude were stretched to cosmological scales, I was telling you the truth, but not the full truth. The thing is that the inflaton field is contributing to the energy momentum tensor on the right-hand side of the Einstein equation. On the left-hand side of the Einstein equation, you have gravity, you have the metric, which is also quantum fluctuating. Now, the scalar part of the metric, you can distinguish a scalar contribution to the metric, a factorial contribution, and a truly tensorial contribution. The scalar part of the metric is fluctuating in sync with the scalar inflaton field, because you can decompose the Einstein equation into a scalar part, a vectorial, and a tensorial part. And so the Einstein equation links the quantum fluctuation of the inflaton field to the quantum fluctuations of the metric itself, to the scalar part of the quantum fluctuation of the metric itself. And it turns out that they are not strictly distinguishable. They are dynamically coupled, and depending on how you choose your foliation of space-time into space-like hypersurfaces, you can either say that all the fluctuations are entirely fluctuations of the inflaton field, but you can also choose a different foliation of space-time into space-like hypersurfaces, such that all the fluctuations are quantum fluctuations of the scalar part of the metric. There is a linear combination of the two, of the scalar metric fluctuations and the inflaton fluctuations, the so-called Mukhanov variable, and which is really a field. And that linear combination is gauge independent. That is giving you the same value independent of how you do your slicing of space-time into space-like hypersurfaces. And yeah, so since they are so intricately linked, dynamically basically the same, when we say that we see the temperature fluctuations in the microwave background, we mean that we see really the imprint of the fluctuation of the inflaton field, but it's indistinguishable from the imprint of the scalar fluctuations of the metric. Same thing. So, in a very real sense, we've seen some fluctuations, and our structured inhomogeneities in the universe are due in large part to, or entirely, to quantum fluctuations of the inflaton field and of the metric, and you can't really distinguish between the two of them. So it's justified to say that it's metric fluctuations as much as it is inflaton fluctuations. Yeah, and then the tensorial, the gravitational wave fluctuations, they are tensorial in nature. That's Weyl curvature, and that Weyl curvature is not scalar, but Weyl curvature is truly tensorial. That is separate. It has its own degrees of freedom, and these are the ones you want to see. Haven't seen yet. If we can find out how strong it is, the relative strength between the quantum fluctuations of the Weyl curvature of the gravitational waves, the depolarization, the curl polarization in the microwave background, the relative strength of it compared to the size of the fluctuations of the scalar fluctuations, just the temperature fluctuations, tells us a lot, or will tell us a lot, about the inflaton potential and the details of what went on there. And if we can even measure the spectrum of the tensorial waves, of the gravitational wave, in the polarization spectrum, then we get even more. There's a highly non-trivial so-called consistency condition that is intrinsic to all inflationary theories, and that prediction and that relationship between the amplitudes of scalar and tensor fluctuations and their spectrum would have no reason to hold if it weren't for inflation. And I think that the moment that's measured, Nobel Prizes will be given for inflation, because then it's clear that it's a very non-trivial prediction. But we need the repolarization, we need the curl polarization of the cosmic microwave background to check that.
You kind of answered my question, right? So.
I did, okay. So it was covered somehow.
So gravitational waves are part of this 1 over r piece of the Weyl tensor, right? Like
yes, they are not near field, they are far field.
Right. So when we talk about gravitational disturbances being blown up, frozen in the CMB, what about near zone stuff? And would they cause only B-mode polarization?
The primordial gravitational waves have a very interesting origin in that they are not caused by the usual method. The usual method would be a planet going around a star, or even more efficiently, 2 stars going around each other, or even more efficiently, 2 black holes going around each other. That's a quite efficient method for gravitational wave production. And in this case, you have a near field, when you're really close to the 2 sources, and you have a far field, just like in electromagnetism, where if you're very close to the antenna, you can tell, oh, there's a current now going up the antenna, and there's charges at the bottom of the antenna, and stuff like that. But if you're sufficiently far away, you can no longer tell that, because that electrostatic, magnetostatic information decays very quickly, and you can only tell, well, there's some antenna, it radiates stuff, right? So you only see the path. So similarly, gravitationally, if you're close to a binary source of gravitational waves, you can learn something about the arrangement of those masses from the near field. Now, gravitational waves that are primordial and caused by inflation don't have an origin in the near field. They never had a near field associated to them. They just came into existence through quantum fluctuation. So they weren't sourced by matter moving, but instead they just came into existence as quantum fluctuations that couldn't snap back. Quantum fluctuations that were ripped apart became very large, and then, it's a non-trivial thing, normally quantum fluctuations, whether they are big or small, could just snap back. If nobody observes them, then they were just fluctuations, right? But the point here is that quantum fluctuations happen all the time, and during inflation, large-scale fluctuations large amplitude fluctuations acquire a large wavelength. And then inflation ends. When inflation ends, all the energy that was in the inflaton potential goes into the production of elementary particles. See, the inflaton field you can consider as having a particle associated to it. And that particle at the end of inflation was decaying. And those particles were decaying into all the standard model particles. Lots of energy went into that, so you have a universe that's filled with hot plasma. And those particles then were observers of the inflaton field. So they decohered the inflaton field. So that means that those fluctuations then became real fluctuations. And that was the origin of these waves. Of both the polarization, it affected the polarization later when the CMB was released, 100,000 years later. But initially, it was just an imprint on the curvature of space-time. So you had the inflation is thought to have ended in a flash, in one moment. Inflation ended when the potential eventually dropped down to zero pretty quickly. It's thought that the potential was slowly going down to potential and quickly going down to potential. And then suddenly all the energy went into the production of particles. And what was previously virtual fluctuations of a quantum field became real fluctuations in an energy density. And then from the end of inflation onwards, for the next 100,000 years, the universe was filled with a hot gas. It was cooling down. It reached, when it reached about 1,000 Kelvin, on the order of thousands of Kelvin, then it was cool enough for protons and electrons to form hydrogen, and then the CMB was released because photons no longer scattered off the charges. They only saw neutral hydrogen, so the CMB. But during those 100,000 years, between the end of inflation and the cosmic microwave background forming, the universe was basically a noisy place because it was filled with this hot plasma in which waves were propagating, namely waves caused by the inhomogeneities that were imprinted on it, on this plasma at the end of inflation. It's just like a drummer having drummed on this thing at the beginning of that time period. So inflation ended, homogeneous, hot gas, and imprinted on it are inhomogeneities. So wherever there's overdensity, the matter will go out, and whereas an underdensity, matter will move in. In fact, it's actually tensorial too. And what is that? It's sound, right? If you have pressure and that's equilibrating, that's sound. So for 100,000 years, you had this sound of the quantum fluctuations, the sound that was generated by quantum fluctuations, propagating through the universe, through that plasma. And so the initial spectrum of the quantum fluctuations is no longer what you measure at the end of that period. The CMB is not showing exactly the spectrum of the quantum fluctuations. It's showing the sound after propagating 100,000 years through a rapidly cooling plasma. But that can be calculated. There's even code for that. You can just plug in an original quantum spectrum, and then you get out the CMB spectrum. And you can do it backwards and forwards. And so from the observed spectrum, you can calculate backwards what was the fluctuation spectrum in the field. And amazingly, it matches very nicely. See, we can create plasma that's very hot. 1,000 degrees is nothing. If you translate the energies available at CERN into the collision energies of a hot gas, you would have something like 10 to the 24 Kelvin or so. It's just temperature that's way beyond anything any stove can possibly do. And so we basically, what this means is that we know plasma physics pretty well. And so it's no mystery, it's known physics that gets us from the end of inflation, or from almost the end of inflation to the ceiling.
So that gap can still be pretty big, right? Because, for instance, what we produce at CERN is 2GP. And 2GP is something that's like around confinement scales and stuff like that, right? And then if you think about the input on that, something really close to the Planck scale, there's like a gigantic gap of energy, right, between that can be like
yes.
dark matter, weird
yes,
particles.
the thing is, there's a lot going on there, and I think the most tantalizing thing is that, I mean, those phase transitions really have it in them. I mean, there's a lot going on, and the formation of defects is just one thing that we'd like to understand better. But another thing is the imbalance between matter and antimatter must have happened there. The inflation is not producing an imbalance between matter and antimatter. It has been conjectured long ago by Russians, mostly, I think the earliest was Andrei Sarov, that what you need is that in the laws of nature there is some time inversion asymmetry. So that, you know, not every process that can occur forward in time can occur also backward in time. If you have that, together with the phase transition, then you can break the particle-antiparticle symmetry. And that could lead to a slight, ever so slight excess of particles over antiparticles, and the rest annihilates. And that's how it's thought to have happened. In fact, the standard model of particle physics has T violation. The T symmetry is not a symmetry of the standard model. And so there is also P violation, and yeah, it is possible, but that's just a matter of it is possible. But how exactly it happened, I don't know. Very hard. Right, so I hope to see you next term. Also, if you like anything about my course, if some of you perhaps could go on the Rate My Professors thing, leave a comment there, or just tell me also for feedback. But the Rate My Professors thing, last term I taught calculus, and there was this one student who hated me. Stuff on Rate My Professors.
It's a quantum fluctuation.
Yes. Yeah, I had 370 students. I taught 2 classes of calculus. And you know, you've got to have a few students who hate you. There's so many, right? Anyway. But you see, I know, actually, I didn't know why. I mean, he was.